Hello and welcome to IONICON. Today, we're excited to present one of our latest innovations, a breakthrough solution addressing the humidity dependence of certain components in PTR-MS. It has been well known and studied that the quantification of various compounds using proton-transfer-reaction mass spectrometry can be influenced by the humidity of the sample gas. For instance, if the concentration of a specific substance in outdoor air remains constant, changes in weather and humidity can still affect the measured signal intensity. Until now, countermeasures have included labor-intensive calibrations at various humidity levels and subsequent data corrections. Other methods have involved using filters or membranes to dry the sample air, which can inadvertently trap important analytes. A common approach is to introduce excessive humidity into the reaction area to minimize relative humidity changes, but this can disrupt established ion chemistry and compromise quantification accuracy. To encounter this humidity dependence problem, IONICON has now developed a novel solution which literally comes without any drawbacks, does not require any additional labor by the user, and does not diminish analytes of condensable nature. So far, a typical IONICON PTR-TOF analyzer consists of three crucial parts: an ion source for reagent ion production, a reaction region or drift tube for chemical ionization, and a TOF analyzer for requiring full mass spectra in split seconds. In the most common H3O+ ion mode, water vapor from a water reservoir is introduced into the ion source. There, a proton is attached to the H2O, producing extremely pure H3O+. The sample gas is continuously drawn into the drift tube where proton transfer from H3O+ very efficiently ionizes VOCs. Finally, the ions are mass separated and detected in the TOF analyzer. Let's take a deeper look at the proton transfer process from H3O+ to an analyte and discuss the conditions necessary for it to occur. The key factor here is the proton affinity, since proton transfer from water to an analyte can only happen if the analyte's proton affinity is higher than that of water, which is 691 kilojoules per mole. Luckily, for a large number of molecules, this is the case. However, for molecules whose proton affinity is only slightly higher than that of water, a significant effect comes into play, namely, a backward reaction can occur, where the protonated molecules can transfer the proton back to the abundant H2O, present in the reaction region. As a result, the ionization efficiency becomes dependent on the sample's humidity. As an example, let's take a look at formaldehyde, which is one of the most manufactured chemicals with an annual production of more than 20 million tons. It also occurs in nature as an oxidation product of terpenes and as a metabolic product of bacteria. It is classified as carcinogen, making the study of this chemical of great significance. Formaldehyde has a proton affinity of 713 kilojoules per mole, so very close to that of water. For a proof of concept, let's start a simple experiment, utilizing our liquid calibration unit LCU and one of our standard PTR-TOF instruments, in this case, a PTR-TOF 10K. The LCU generates a well-defined trace gas mixture by evaporating a standard solution into clean air, enabling precise calibration. In this setup, we produce a constant concentration of formaldehyde in zero air, while water is introduced via a liquid inlet port to adjust the humidity level. Since the proton affinity of formaldehyde is so close to that of water, we observe the following. First, we look at the H2O-H3O+ cluster signal, which we use here as an indicator of humidity in the drift region, which increases as we raise the relative humidity correspondingly. At a first humidity level, we detect a certain ion yield for formaldehyde. Then we increase the humidity, and accordingly the cluster signal rises. At the same time, the formaldehyde signal goes down. Increasing humidity even further leads to further decrease in the formaldehyde signal. Finally, we turn off the humidity supply, the cluster signal falls, and the formaldehyde signal increases significantly. This step-by-step change confirms what theory predicts: the measured ion yield of formaldehyde is strongly dependent on ambient humidity. There are already common countermeasures against this effect. That is either calibration of all compounds of interest at various humidity levels, which can be very elaborate, or the installation of filters or cold traps in the sample inlet line, which can lead to possible depletion. Hence, so far each solution comes with considerable drawbacks. Therefore, IONICON now came up with a very simple but highly effective solution. To explain the principle to you, let's have a look at our PTR-TOF setup again. As we already discussed, the crucial moment takes place in the reaction region, where the proton is transferred from our H3O+ to the analyte. Now we modify our setup by installing two T-pieces, one in the gas line between the water reservoir and the ion source mass flow controller, and the second one in the sample inlet line close to the reaction region. Consequently, the two T-pieces are connected via another mass flow controller. Via monitoring the H2O-H3O+ cluster percentage to get information on the current humidity in the reaction region and a PID module in the instrument's control software, a target humidity can be chosen and the water vapor flow can be automatically adjusted. Back to the lab, let us repeat our experiment, but now we use our new modified setup and control the humidity in the reaction region, while again varying the added water vapor flow in the same way as we did before. Again, we start the experiment at a low level of relative humidity. Then we increase the humidity to an intermediate level. Then increase even further until saturation is reached. And finally, the humidity supply is turned off. We now see that despite the varying humidity, the formaldehyde signal remains constant. So we see that, via the controlled injection of water vapor into the reaction region, the humidity is kept constant throughout the analysis, independent of the sample gas constitution. Therefore, any changes in the acquired ion signal intensities reflect real concentration changes, and, if ever required, calibration measurements only have to be performed at one humidity level. With our innovative setup, quantification is now completely independent of varying sample humidity. This groundbreaking method eliminates the need for time-consuming calibration series and data corrections, as well as the risk of selective compound suppression from filters and membranes. Explore the possibilities on our website ionicon.com. There you will find countless applications where IONICON PTR-MS technology serves as an invaluable tool for real-time quantification of extremely low concentrations of compounds. Browse through our extensive collection of application notes and diverse product portfolio. Thank you for your attention. We can't wait to hear from you.